Welcome to this video about confidence intervals for 2RH. You need to take a deep breath because this is gonna be a monster video. It's gonna be longer than the usual ones, and that's because when you do confidence intervals for 2RHs, you actually also sometimes need to make a hypothesis test. So we are going to combine the confidence intervals and hypothesis test in this specific video. This is a formal way of working with the confidence intervals. So it's not something we just can skip. It is part of you can say, confidence intervals. But if you are unaware of how a hypothesis test works, you can always just go to the hypothesis section and rehearse a bit there, or see some videos on the concept of hypothesis testing. I would probably advise you to just watch the video, and if it seems a bit blurry when you get to the hypothesis testing, just live through it, and then by the end of the video, you can, if it's all like a mist, go to the hypothesis section. Otherwise, it should make a relatively good sense. So let's just start. Let's assume we have this ad agency that has developed a method to identify the most effective ad. Now, this agency has been working a long time for Google and has narrowed down the choice to 2 ads. Each ad has been tested on a 10-point scale, and the results is what you can see in the box here. So ad 1 had an average of 7.1, a standard deviation of 1.7, and a sample of 29, whereas the second ad has the data you can see below here. So there is like a difference in the sample size. Sometimes when the respondents are difficult to get or very expensive, or that is often the same thing, then typically we don't have a huge sample. So that is the answer of why are they not equal, those two samples here. Now, since this ad 1 is considerably cheaper to produce, Google of course would like to know, based on statistics, if there is a significant difference between the 2 ads. It looks as if ad 2 is a bit better, but this could just be randomness, right? So we're gonna make you can say a confidence interval for the difference between the two average scores, and then based on that confidence interval, we will see if we can comment which one is best. Or let me rephrase: we will comment on if ad 2 really is better than ad 1, or if this is just randomness. So let's go to the blueprints. We are dealing with an average. And the first question is, are both samples larger than 30? And they are, in this case, not, because one is 29. So here we have to go to the next one here, is the population variance known? And in this case, no, we don't have a known population variance because it's just based on the samples, right? So we don't have any known population variance. So that means that we need to test for variance homogeneity. In simple words, it just means that we need to test if the variances of ad 1 and ad 2, if the variances of the ratings could be the same, or if they are different. Variance homogeneity just means sameness. So we will go into the StatLearn here, and scroll down to the test where we have hypothesis testing 2 samples, and we will go to testing for difference between 2 variances here. I'll just delete the prior data here. And then we have 29, and the standard deviation for this one was that was 1.7. Yes, so I'll just go back 1.7, and the other one was 2.4 and 51 here. It's very simple when we test. I'll just delete the variable here. We'll change that. So this will be ad 1. We'll just put ad 1 ratings like this, and this would be ad 2 ratings, right? Maybe I'm making an error here. It's no, it's fine. It's good. So we are always putting it in H0, as you can see here, the one equal the other when we're testing for homogeneity. So this is a no-brainer. We don't have to think. We just have to put it here, and everything will be fine. Okay. So this tells us the p-value here. This is, once again, if you haven't done hypothesis testing before, it will be a complete black box this here. But as mentioned, you can just go to the section about hypothesis testing and you will know relatively soon. But since the p-value here is higher than the test level, we are accepting H0. And that means that variance A can be said to be the same as variance B. So in this case, we go back to the blueprints and we say, yes, there is variance homogeneity. So that means that we can go to the pool T confidence interval. Have no idea why that's the name, but that's how it is. Let me just check here, back to the menu. And yes, so confidence intervals for, where is it? Equal variances, here it is, right? So just go in here, sample 1, sample 2, 51, and this was 1.7, right? And this was 2.4, if I remember it right, and the R1 was 7.1 and 7.9, wasn't it? Something like this. 7.1, yeah, exactly. So if we go here, 7.1 and 7.9, this is just standard, we'll just leave it here, unless it is explicitly stated that you should do a confidence level of 99%, just always go with the default 90 and 95, okay? And rating of @1 and rating of @2 here. We have the data here. And the assumptions is stated we are having equal variances, variance homogeneity. This is a killer formula. I will not go into the details here, but this is the, you can say, behind the curtains. This is the model that is used to obtain the results we get here. Now, we have an interval, and this is very important to know when we do a confidence interval for the difference between two averages. This interval here is not an average, it is the difference between average 1 and average 2. Sometimes people misunderstand it and think this is the average for @1 or @2, but this is the average difference between @1 and @2, okay? When this interval is crossing 0, so when the lower is negative and the upper is positive, it means that we cannot say that there is a difference between the two averages. So based on this result, we can say that there is a 95% probability that the average rating of @1 and @2 are equal or is the same. So based on these results, we cannot say that that Google should go for @2, even though it seems to be better, because there is no significant difference between @1 and @2.